Okie dokie, friends. Time now for a lesson on area between two curves. We have used the integral to find the area between one curve and the x-axis. On today's show, area between two curves. What happens when one curve is on top, another is below, and we're looking for the area between them. So let's talk about what we mean by that. I want to do it from a theoretical standpoint and then from a practical standpoint. So you've got two functions. He's up here and she's over here. Oh, let's make a different her. She's over here. And I want to find the area between them. I want to find the area in between the blue graph and the red graph. And so what we do theoretically is we divide up the region into a whole bunch of approximating rectangles. And the area of each rectangle is length times width. The length is f at some special place minus g at some special place, and the width is a teeny tiny change in x. And so what we do is we say, well, we'll just put a whole bunch of these rectangles together. We'll get a whole bunch of rectangles. Maybe some will look like this, and some will look like this, and this one over here looks like this, and this one over here looks like this. We add them all up, and that's approximately the area of the shaded region, the area between f and g. But here's the thing. We don't want an approximation. We want an actual area. And to get an actual area, you need smaller and smaller rectangles, thinner and thinner rectangles. So we line up infinitely many, infinitely thin rectangles. And so as delta x gets closer and closer to 0, we get the area equal to an integral from a to b, where this is a and this is b. F of minus g of becomes f of x minus g of x, and the teeny tiny change in x is a dx. So really we have the same process that we used for area between one curve and the x-axis. We take a whole bunch of approximating rectangles, make them thinner and thinner and thinner, take the limit as the number of rectangles gets infinitely large, and we get integral function minus function, top minus bottom, dx. And that's exactly what we're going to do right here. Find the area between y equals 2 minus x squared and y equals negative x. If you're unfamiliar, 2 minus x squared looks like this, and negative x looks like this. And so we're looking for this region right here. You can use algebra and figure out that this x value is negative 1 and this x value is 2. I will not bore you with the details on that. Except to say that 2 minus x squared would have to equal negative x. So x squared minus x minus 2 would have to equal 0. And algebra takes you home tonight. I want the area between the curves. So to figure out the area between the curves, I set up the definite integral from negative 1 to 2 of top minus bottom dx. And so what have I got? I take an antiderivative. You should make sure that that is actually the antiderivative in question. We substitute 2. We substitute negative 1. We subtract. And there it is. Area between two curves. We integrate top minus bottom. Boom. Find the area bounded by y equals 2 cosine x plus 1 and y equals x squared minus 2. This is a little bit more tougher, so let's bring in the big gun. Let's take a picture. 2 cosine x plus 1. No, plus 1. Very good, yes. I have a master's degree. And then x squared minus 2. Graph. Graph. Zoom. Probably too far. There. Picture. This is the picture we're dealing with. So y equals 2 cosine x plus 1 is this function. Y equals x squared minus 2 is this function. I want the area in between them. To figure out the area in between them, I need to integrate top minus bottom dx from the first place they meet to the second place they meet. From the first place they meet to the second place they meet. Well, luckily, I can find intersection points. Bam, bam. Take a guess. Close enough. Bam. That's 1.672. Now, in truth, you're going to write that down to a bunch of decimal places because when you fnint the thing, you're going to have all those decimal places in place. Similarly, the lower limit is negative 1.6724413. And so you are going to say, I want the integral of 2 cosine x plus 1 minus x squared minus 2 dx from negative 1.6724413 to positive 1.6724413. Well, golly. I'll take a picture because it lasts longer. And that's 10.895 rounded to 3 decimal places. As a side note, you could say, since you already have those functions in your calculator, you could hit the vars button. That stands for variables. And you could hit the right arrow over to y variables, and you can say the function y1 is that cosine value, that cosine curve, minus vars, y vars, the function y2 with respect to x from negative 1.6724413 to positive 1.6724413 and get the same answer as before. That's a sort of a big deal, actually. So just things that you want to know how to do on your calculator because they matter. Yes, that looks good. Okay. So what happens? Blow it up. There we go. What happens if the shaded area involves 2 curves? Well, 3 curves. We're going to have y equals the cube root of x, and we're going to have y equals 1/2 x minus 2, and I want that area. Now that's a tougher go. And that's a tougher go because if I take my approximating rectangles In this region, they go from the blue curve to the black line. But if I take my approximating rectangles here, they go from the blue curve to the red curve. So I actually have to draw a line of demarcation at x equals 4 and say we need two separate integrals. We need an integral of area 1 and an integral for area 2. And so the area I want is going to be the area of 1 plus the area of 2. What's the integral that'll help me find area 1? Well, it's just from the blue curve down to the black line, so that's the integral from 0 to 4 of cube root of x dx. But then when I'm interested in area 2, that's from blue curve to red line. And blue curve to red line is top minus bottom from 4 to 8. This is 8. And if you were to crank that out, I bet you could. Antiderivative of x to the 1/3 is x to the 4/3 divided by 4/3, evaluated between 0 and 4, plus 3/4 x to the 4/3 minus the antiderivative of 1/2 x is 1/4 x squared. Antiderivative of 2 is 2x from 4 to 8. And if you crank all that out in the privacy of your own home, that's 8. So we've got to make sure if we're going to do top minus bottom that our top is always the same all the way across and our bottom is always the same all the way across. But I wonder if we could have done this problem differently. So I'm going to bring it down. We're going to bring this thing down. I wonder if instead of, let's ungroup, instead of vertical slices, what if we used horizontal slices? What if we decided that our approximating rectangles were going to go like this instead? Because if we use horizontal rectangles, then the process is the same. We use approximating rectangles, we make them thinner and thinner and thinner as there are more and more and more of them. And we're always going from the red line to the blue curve. We could do it with one integral. The problem is it's a dy integral because the width of my rectangle is a teeny tiny change in y. And because it's a teeny tiny change in y, we need a dy integral, which means we need our x's in terms of y. So if I solve that, x in terms of y, and then I solve this, x in terms of y, then when I go to find my integral, I'm going to go from the smallest y value I have to the largest y value I have, not of top minus bottom, but of right minus left. Not top minus bottom, right minus left. And so that's y squared plus 4y minus 1/4 y to the 4th, evaluated between 0 and 2, and that is much more obviously 8. So it may be helpful to you to give that a go. If you can slice horizontally, it is sometimes to your advantage to do so. And we'll talk about that more when we get together tomorrow. I'll have a couple of things for us to do together as practice before we break up and work individually. All right, everybody. See you tomorrow.